Good to see you, everyone. So in this second talk, I will talk about generative modeling. So first question, who has used ChatGPT or anything like that? Maybe everyone, right? But who have heard the term of generative model before you got to know ChatGPT? Well, still quite a lot. Yeah, so in this talk, I will give very high-level overview of what generative modeling is and how it's impacting our life and our future research. So there is no doubt that we are in the so-called Gen AI area. So for public audience, perhaps this moment happens when ChatGPT or many other chatbots were introduced. So you can communicate with the computer in natural languages. You can talk. You can ask the computer whatever problems, and it's just like an agent that can help you to solve many issues. So this is not the only generative AI model. So another very popular and very powerful tool is the so-called text-to-image generation. So for example, the users can give the computer some text, which is usually called a prompt, and then the computer can generate an image. So, for example,
change the adapter.
Let me remove this. Okay, I hope it works. Okay, sorry about that. So for example, in this case, the prompt would be a teddy bear teaching a course with generative model written on Blackboard. So it is very likely that the computer algorithms hasn't seen this exact image before. But this is how it can produce from the given text prompt. So we can even go one step further. We can ask the computer algorithm to generate a video, and this is what is generated by Sora 1 year ago. So this is just really impressive. So I believe perhaps no producers have ever take a video in this way, having so many paper planes flying on top of trees or forests. So this is completely generated by kind of the imagination of the computer algorithms. So actually, generative models could be very powerful, productive tools in our daily life. For example, it's still kind of a chatbot, but it is a chatbot that can help us to write code. So this is kind of an AI assistant. So it can read your code, it can try to fix the issue of your code, and you can directly communicate with the agent using natural language, and the agent will turn it into code. So in some sense, perhaps the previous programming language is C++, Python, or Java. The next level of programming language would just be English or human language. So it's more than that. It's more than just computer science. Actually, generative models has been used in many scientific problems. So this is an application which is called protein design and generation. So the ultimate goal is to design or generate some type of proteins that can solve some problems that we care about. Let's say cure some very dangerous, very fatal diseases. So this work is called RF diffusion. It's actually part of the work of the Nobel Prize winner this year. And there are many other scientific problems that can benefit from generative modeling. So this is a work from DeepMind a few years ago. So they can use this model to predict the weather change over the next several hours or next several days. So this would be a very difficult problem for classical algorithms because, as we may know, the change of weather or the change of climate is chaotic. So it is very difficult to predict it precisely. So we may not want to have the exact physical state of that moment. What we want is some qualitative behavior, let's say whether it's raining or whether it is windy at that moment. And in this sense, generative models or deep learning could provide a very good solution to this problem. So actually, before the recent emergence of generative models in our daily life, actually generative models have been used or developed for decades. So this is a tool which is called a patch match, or that is called as content-aware fill in the software Photoshop. So it was a very impressive tool when I was a PhD student, and at that time I worked exactly on the same problem. So the problem here is that you will be given a photo and the user can specify some area or some structures in the photo, and the computer algorithm is trying to fix the photo or edit the photo based on the user instructions. So actually at that time there is no deep learning, and to be honest, for this application or for this algorithm, there is even no machine learning. So it is a very classical computer vision algorithm. But conceptually, this is also a kind of generative modeling. So the technique behind this generative model actually can date back even another 10 years ago. So this is an algorithm that is called texture synthesis. The goal here is that you will be given an example texture and you want to extend the texture to a bigger image, or you want to paste the texture to some 3D objects that you care about. So the idea here is just very simple. You just try to synthesize the texture pixel by pixel based on what has been synthesized. So in today's world, this is actually an autoregressive model.
You might know Harbor Freight for affordability. What you might not know is performance and durability go right along with it. You see, we test, and then we test again. World-class engineering and rigorous testing to ensure our tools perform at the highest level and stand the test of time without testing your wallet. Now, it's time for you to put us to the test. Whatever you do it for less at Harbor Freight.
Okay, so then this is basically what I'm going to talk about in this talk. I will very quickly go through the concepts of what is a generative model. And then I will introduce some approaches, some modern approaches to how we can build generative models using today's deep neural networks. And then I will also talk about how we can formulate real-world problems into kind of generative modeling. Okay, so first, what are generative models? So it turns out this is a very difficult question because when the generative models becomes more powerful and more powerful, the scope of the generative models keep changing. So even though I will talk about some classical definitions of generative model, I just want to say perhaps today every single problem could be formulated as a kind of generative models. So now let's look at the applications or scenarios we have just introduced. So what do these scenarios have in common? So for example, in image generation or video generation and text generation, actually there are multiple predictions or actually conceptually infinite predictions just to one input. Let's say if you want the computer to generate an image of cat, so you will tell the computer, this is a cat, I want a cat. And conceptually, there is an infinite number of possible cats. So another property of generative model is that some predictions are more plausible than some others. So for example, if you want, let's say, a cat, and then the computer may generate a lion, or it can also generate a dog. And then perhaps in common sense, a lion is more plausible than a dog in this scenario. Of course, a cat is more plausible than a lion. And another very intriguing property of generative modeling is that your training data may not contain the exact solution. So as we have seen, I believe the computer has never seen a teddy bear standing in front of a black box and teaching generative models. And similarly, the computer may not, must have not seen these paper planes flying on top of forests. So this is kind of an out-of-distribution generation. So the computer algorithms were trained on some data, but what they are generating is some distribution that could be outside of the training data. So in addition, most of the time, the predictions of generative models could be more complex and more informative, and conceptually it is higher dimensional than their input. So for example, in text-to-image generation, if you want a computer to generate a cat, which is just a very short word, and their output image would have millions of pixels or maybe even more. So all these properties make a generative model way more difficult than some of the classical deep learning or recognition problems. So in a textbook, this is kind of formal definition of what would be a generative model. Usually, when generative model is introduced, people would compare it with a so-called discriminative model. So what is a discriminative model? So typically, as you have seen in Philip's talk, if we care about an image classification problem, you would be given an image, then you are going to train a model, for example, a neural network, then you want a neural network to output a label, let's say a dog. And conceptually, in this very simple scenario, we can just imagine generative model as reversing this process. So in this case, you would be given a dog, and then you would like to train a model, again, which could be a neural network, and then you want to output the image, which is X. So in this case, there would be many possible outputs, many possible dogs. The output would be higher dimensional, and the output would be another dog that you haven't seen before. Then, conceptually, this is kind of a probabilistic visualization of what would be a discriminative model and what would be a generative model. So, on the left-hand side is a discriminative model. You have some green dot, which is one class, and some orange dot, which is another class. So the goal of a discriminative model is just to find a boundary that can separate these two classes, which seems easier. Then conceptually, the task is try to find out this conditional probability distribution, which means you will be given X, such as an image, then you want to estimate the probability of Y, such as it is a label 0 or label 1. Then as a comparison in the context of a generative model, you would still be given the same data, the same dot. But the goal here is to estimate the probability distribution of this dot. Let's say in the case of this class, which corresponds to y equals to 1, you want to estimate what is the conditional probability distribution of this class. So conceptually, in a generative model, we care about probabilistic modeling. So that is the key problem a generative model wants to address. And that is also the key challenge. So you may wonder why there's probability and why we care about probabilistic modeling. And actually, in many of the real-world problems, we can assume there are some underlying distributions. And you can also assume your data is actually generated by some very complicated word models. So, for example, if we care about human face images, we can formulate the problem as there would be some latent factors such as the pose, the lighting, the scale, and actually the identity of the face. So this would be the latent factors. And then you assume there will be some distributions about these latent factors. And these latent factors would be rendered by a word model. So that is, for example, how you can project a 3D object onto a 2D grid of pixels. And then these latent factors would be rendered by this word model, and what you can actually observe is just a 2D grid. So that is the observation X. Then your 2D grid would follow some very complicated distributions that cannot simply be described by some underlying distributions. So this is why we care about probabilistic modeling, and a generative model is trying to uncover these underlying factors or to reverse this process.
So being a new parent and living on Long Island and owning a business here is super expensive. Hi, I'm Jared Bell, and right now we're standing at our family business. We have a bagel and bialy manufacturer. Actually, I'm third generation.
Now, so for example, let's say we have some data. Let's say I have a data set of dogs, which means I have many data points, and every single data point would correspond to one image of a dog. Then conceptually, we imagine there is some underlying distribution that can model the distribution of all dogs. So it's worth noticing that this is already part of your modeling because you can model the underlying word generator in many different ways. So even though we often assume there is this underlying distribution, this distribution is a part of the modeling. And then the goal of generative modeling is to learn a neural network, or perhaps another model, to approximate this distribution. Let's say this red distribution is what we can learn from a neural network, and the goal here is to minimize the distance between the data distribution and the distribution you estimated. This is still a very difficult problem. There are many solutions to this problem, but conceptually, almost all existing generative models could be formulated in this way, and they are just trying to address the challenge exposed by this problem. Then conceptually, assuming your model has done a good job of this, then you can start to sample from the distribution you estimated. So if your model is doing a good work, that means when you sample from this distribution, you would be doing something that is conceptually similar to sampling from the original data distribution. Then in this case, hopefully, it will produce another dog that your algorithm haven't seen. Then it is also possible to do the probability estimation. So that is, your model would be given another image, let's say a cat, and then you can ask the model how likely this image is under the original data distribution. Then in this case, if the original data distribution are about dogs and the input image is a cat, then hopefully it will produce a low estimation of the probability density. So this is kind of how we can use probability modeling to formulate the generative modeling problem. Then, as you can imagine, the most powerful tool today for us to address generative modeling is deep learning. So Philip has given a very excellent and very quick introduction of what deep learning is. So conceptually, in a nutshell, deep learning is representation learning. So what Philip has introduced is a process of learning to represent the data, or conceptually the data instances. That means you will be given the data, let's say the images, and then you want to map the images to labels. So this is one way of using deep neural networks for representation learning. Then in the case of generative modeling, actually there is another way of using deep learning, but still for the goal of representation learning. So that is, we don't just want to learn the representation of one single data instances. So we want to learn the representation of a probability distribution. So that is a more complicated problem, and conceptually, it can be viewed as learning the mapping the other way. Let's say here, the output would be the labels, let's say the label of cats or the label of dogs, and then you want to map it back to the pixel space. So then, as you can imagine, deep learning or deep neural networks is a very powerful tool for generative modeling. And conceptually, when you use this tool for this problem, the models are actually simultaneously playing these two roles. So first, learning to represent data instances, and second, learning to represent probability distributions. then this is conceptually what a model would look like. So your model would be given a very simple distribution. For example, it could be a Gaussian distribution or it could be a uniform distribution. It doesn't matter. So in the case of an image, this would look like just a completely noisy image. Then the goal is to learn a neural network such that it can map a noisy image to just another image in the output space. Then conceptually, if your model can do a good work, hopefully the output would be a visually reasonable image, such as a dog in this case. Then you can just keep sampling noise from the input distribution, and hopefully the neural network will turn everything into some meaningful images in the output. Then conceptually, when you do this, actually your neural network is trying to map a simple distribution, let's say Gaussian distribution here, to another distribution, which conceptually is to approximate the underlying data distribution. Then in this sense, a generative model is a mapping between distributions. It is not just a mapping between a pair of data points and a label. It goes from one distribution to another distribution. The next slides would be a little bit technical. Perhaps I can go very quickly. So these are some of the fundamental elements of a deep generative model. So first of all, you may need to formulate a real-world problem as a probabilistic model or a generative model. This is kind of one of the most critical parts for us to design an algorithm. And after you can do that, you need some representations. And today, usually this is a neural network. So you want to represent the data and their distribution. And then you need to introduce some objective functions to measure the difference between two distributions. And then you need an optimizer that can solve the very difficult optimization problem. And then you also need an inference algorithm, which is conceptually a sampler that can sample from the underlying distribution. Today, many of the mathematical or theoretical research would be about one or many elements in this list. So I'm not going to delve into the details.
With the Planet Fitness Black Card, you'll get your first month free when you join today. Sign up for just $1 down, $29.99 a month, and get your first month free.
Hurry, you won't want to miss this exclusive offer. Deal ends March 13th.
What's he like? The happy-faced killer?
You mean my dad? Be glad you never have to know.
You think that you're so much better than me.
You're just like your old man.
I'm not like you at all.
But next, I'm going to give a very high-level and very quick overview of what are some of the modern approaches and popular approaches to generative models. And I'm also going to explain why a generative model is a hard problem. So this is the figure you have just seen. So as you can see, the problem here is that if your model would be given one noisy image or noisy input, you want it to map to map the noise to an output image. So why this is hard? So recall that in Philip's talk, he has talked about the problem of supervised learning. So in that case, you would be given one image and also a label of that image. So you have a pair of input and output. So that is a very well-formulated problem of supervised learning, and that problem is easy for modern neural networks to solve. But in the case of generative modeling, conceptually, it is an unsupervised learning problem. So that is, you will be given an image, but then conceptually, you have no idea what an input noise would correspond to that image. Then this correspondence or this pairing problem is also what your underlying algorithm should try to figure out. So then in this sense, conceptually, it is not just about mapping pairs of images or pairs of data. It's about mapping two distributions. So you want to map a simple Gaussian distribution to a very complicated data distribution. And this is why generative modeling is hard. So there are many effective and very smart algorithms to address this problem. So I will start from some very fundamental and very elegant algorithm, and then I will start to talk about some of the state-of-the-art algorithms today. So first I will talk about variational autoencoders, or VAE. So conceptually, in generative model, as we have introduced, you want to map an input distribution to an output distribution. Then we can formulate this as an autoencoding problem. That means if you will have the distribution of the data, then you can train another neural network to map the data distribution to the distribution you like, let's say a Gaussian distribution. Then you can then after you have this distribution, you can learn the generator to transform it back. Then conceptually, you compute the distance between the inputs and the output. So this is the very classical idea of autoencoding in deep learning. But in classical algorithms, usually conceptually, this would be applied to the concept of data instances. That is, you apply this to every single images. So in the case of variational autoencoder, conceptually, the concept of autoencoding is applied on the distribution. So you can just imagine this distribution is just one object. It's just one entity that you want to process. So you transform this object into this simpler object, and then you transform it back. So then this is the autoencoding idea. Then another very popular solution that is kind of the beginning of research in generative modeling 10 years ago is called the generative adversarial networks, or in short, GAN or GAN. Conceptually, GAN also just want to learn a generator that goes from a simple distribution to the data distribution. But instead of introducing another network before the before the simple distribution, in the case of GAN, it introduced the extra network after you have obtained the estimate distribution. So this extra neural network would be called a discriminator. The goal of the discriminator is to tell whether your sample is from the predicted distribution or is from the real distribution. Then if this discriminator cannot tell which distribution it is from, then it means these two distributions would be very similar. So GAN is kind of the most popular and most powerful generative models over the last decade, until there are some very powerful tools came out over the last 3 or 4 years. So another very powerful generative modeling tool is called autoregressive models. And in the context of natural language processing, this is usually known as next token prediction. But conceptually, the idea of autoregressive or autoregression is more than just predicting the next token. So basically, if we care about probability that involves many elements or many variables, then following the very basic principle of probabilities theory, we can always decompose this joint probability into a chain of many conditional probabilities. So the key idea of autoregressive modeling is to model every single conditional property individually, rather than modeling the entire joint probability. So if you do this decomposition following the order of the sequence, let's say in this case, you want to predict x1 first, and then you predict x2, conditional on x1, and so on and so forth. If you follow this sequential order, then you can turn your problem into next token prediction. So this idea of autoregressive model is to break a very complicated problem into a bunch of simpler and smaller problems.
Why would you assume that there's a lake?
Why would they call it the lake view?
So for example, in this case, in the first output, you will estimate a very simple and lower dimensional distribution. in this illustration, for example, it would be a one-dimensional distribution. And then in the second node, it will predict the next dimension of the variable, then it will be a two-dimensional distribution, and so forth. It will be difficult to visualize a higher dimensional distribution, but conceptually, when you do this, it would be a distribution in a high-dimensional space. So this is the key idea of autoregressive modeling. Then, over the last 3 or 4 years, there is a very powerful model emerging, especially in the context of image generation and in computer vision. So this model was motivated by thermodynamics in physics. So the idea is that you can formulate a problem as repeatedly corrupting the clean data or input image by adding Gaussian noise, and then you can progressively turn it into a fully noise image. And then the goal of learning is to reverse this process. And if you can do that, then you can progressively go from a noisy input back to the clean image. And this idea is called a diffusion, or it is often also called a denoising diffusion. So conceptually, using the terminology of probability or probability distribution, this means you will have an input data distribution. Hopefully, it will be about the clean images. And then you just repeatedly adding noise on top of it. Then conceptually, this is just like running a convolutional kernel on top of the distribution space. And by doing it many times, ultimately, you will turn the data distribution into a Gaussian distribution. So then your model is just trying to learn to reverse this process. So this is what a diffusion model may look like at inference time. It will start from a very simple distribution, say a Gaussian, and then it will progressively reverse the process and go back to the data distribution. So actually, this visualization is very similar to many of the concepts that are popular in graphics. So, for example, you can imagine the starting points of this process is some canonical shape. Let's say it would be a sphere, or it would be a cylinder. Then you want to progressively morph or warp this object, this shape, into another shape that you like. Let's say this could be, for example, just a mountain or a bunny. So you want to progressively warp the input sphere to a bunny, and this is a very well-studied problem. So in the case of distribution modeling, we can imagine this distribution literally as a geometric entity, and then you can formulate a process to do this transformation. And actually, what I have just described is kind of an emerging idea which is called flow matching. So you want to flow from a very simple object or very simple shape, such as a sphere, to another more complicated shape, such as a bunny. And if you have this algorithm, and then if you formulate your underlying shape as some probability distributions, and then you can use this idea to do probability modeling, that is generative modeling. So here, conceptually, this is just another visualization of the same thing. You will be starting from some simple distribution, let's say a Gaussian, and this would be your data distribution that you want to model. The goal here is to progressively change your input distribution to the output distribution. Then there are many excellent solutions in computer graphics to this problem. So one idea here is to learn a flow field. So you can imagine if this is literally a 3D object, then you will have some 3D vertices or 3D surfaces. So you want to gradually move these 3D surfaces from the sphere to some 3D surfaces in your bunny. So then if you do that, then there will be a flow field that can be constructed via this process. So there would be a lot of mathematical details behind, and of course I'm not going to delve into it. But this is kind of the high-level idea of the latest progress in generative modeling, that is flow matching. So conceptually, these are some of the popular approaches today to generative models.
Finding where you fit. LinkedIn knows how.
This is a Maserati logo. There are 61 of them on the Grecale. Why 61? Because 60 wasn't enough. Maserati Grecale.
I haven't covered any of the mathematical details, but it is kind of fun to walk through all these methods. The point I'm going to make is that in all of these generative models, there would be some deep neural networks as the building block. And conceptually, this is just like in deep neural networks, there would be some layers as the building block. So the layers are those modules that Philip have just introduced. So they could be a linear layer, they could be a ReLU, they could be a normalization layer or a softmax layer. So neural networks are some entities that is built by so-called layers. And today, these generative models are some entities that are built by deep neural networks. So in this sense, the generative models are the next level of abstractions. Okay, then next I will talk about how we can use these mathematical models or these theoretical models of generative modeling in the context of solving real-world problems. So as we have introduced, the key problem in generative model is about this conditional distribution. So you want to model a distribution that conceptually you will be given the condition y, and it is about the distribution of your data x. But then in reality, what is y and what is x? In common terminology, y is called the conditions. Let's say you want to generate a cat. It could also be some constraints. Let's say you don't want to generate some type of output images. It could also be labels, text labels, or maybe some other labels. And it could also be attributes. Let's say you want to generate a big object or a small object. So in most of the case, the label, or the condition y would be more abstract, and it will be less informative. And as a comparison, the output x is usually called the data, or it would be the observations or measurements of the samples that you can see in the real-world problems. So in the case of image generation, then usually x is just the image. So usually x would be more concrete than the condition y, and it would be more informative, it would be more higher dimensional. Now let's go through the applications we have just introduced, and let's discuss what would be x and what would be y. In the case of in the context of a natural language conversation or chatbot, the condition y would be the so-called prompt that is given by the user, and the output x would be the response of the chatbot. So usually the output is higher dimensional, and there would be many plausible outputs that can correspond to the same prompt. And similarly, in the context of text-to-image generation or text-to-video generation, the condition would be the text prompt. It could be a sentence, it could be a class label, it could be some attribute. And the output would be the generated visual content, such as an image and video. And the output is higher dimensional, it is more complicated. So these are kind of typical use cases. And of course, this is also the case in terms of 3D generation. In this case, the condition would still be a text prompt, and the output would be the 3D text structures. In this computer vision or graphics application, the 3D text structure would be the shapes, textures, or maybe even illuminations of the underlying object. And then we can move one step further. Then we can generalize the scenario to the problem of, let's say, protein generation. In this case, the input condition could still be some prompt. It could still be some text. Let's say you can try to tell the computer that I want to generate a protein that can cure cancer. So that is valid. But the problem here is that there's no way for the computer to understand what does it mean by cure cancer or what it can do to cure cancer. So in this case, there would be a lot of research in how you can represent the underlying condition that you care about. So you want your output protein to have some properties, and you hope that those properties would be related to, let's say, cure cancer or curing some special diseases. So in this case, the condition would be more abstract. It could also be higher dimensional because it is the abstraction of some behaviors, let's say cure cancer. And the output would be another representation that is also higher dimensional, let's say the protein structure in 3D. It would just be like another kind of 3D object. Then let's talk about some other scenarios that typically people won't think of as a generative model. Let's say this is a very classical case that people would regard as discriminative models we have introduced. So this is, sorry about that, not this one. So this is the typical case of image generation as well. So you will be given a class label, and then your algorithm would be asked to generate the output image. So this is the so-called class conditional case, which means your Y would be very specific about one label. But then there is another scenario where you can imagine you won't be given any conditions. So that means you want to generate the data output that would follow the entire distribution of the data. Then in this case, you can imagine the underlying condition as an implicit condition, which means you want the image to follow the distribution of your underlying data sets. And if your model can do a good job in this regard, so it will try to distinguish the distribution of this data set with the distribution of any other data set.
You mastered your mind. And all the while, you were on the train home. Audible. There's more to imagine when you listen.
You're about to be entrusted with top secret information.
Right now, you can get Disney Plus and Hulu for just $2.99 a month.
Just one of those days, I guess.
Your favorites from Disney Plus and Hulu together on Disney Plus for just $2.99 a month.
This is serious!
Is something distracting you?
That is beautiful.
For a limited time, get Disney Plus and Hulu for just $2.99 a month for 4 months.
Okay, then this is the case I have just confused with. So this is the idea that we can apply a generative modeling to the scenario of discriminative modeling. So here is a very typical case of supervised learning or of discriminative learning. That is image classification. So you will be given an image, and then you want to estimate the label of that image. And if we want to formulate this as a generative model, then in this case, actually Y, which was a label in almost all our previous examples, would be the image in this case. So the image is your condition in this case. And then the class label X would be the predicted output. So you want to model the probability distribution of your output. So just because this model, this problem is too simple and too trivial, and usually people won't think about it as a generative model, but it can be. So then what is the point here? So if you can model image classification as a generative model, then actually you can extend the scenario from closed vocabulary classification, which means you will be given a predefined set of class labels, to the scenario of open vocabulary recognition. That means you won't be given a predefined set of class labels. So that means there could be many plausible answers to the same image. Then in this case, you will still be given one image, but then your output is no longer one unique correct answer. There could be many different possible answers that can describe this image. For example, in this case, these are all reasonable answers to say this is a bird or a flamingo, this is a red color or perhaps orange color. So as you can see, even for this very classical image classification problem, if we try to formulate it as a generative model, it could also open up new opportunities and it will enable new applications. That is non-typical for classical discriminative models. And we can even move one step forward. So you can imagine the input condition Y is still an image, and you want the output not just be a label or a short description. It can be an entire sentence, or it can even be some paragraph that can describe this image. So actually, this is also a classical problem in computer vision, which is known as image captioning. So you want the computer to write a caption about this image. And then with this context, we can even move one step forward. So then this image could just be part of the input in your conversation, in your natural language conversation with your chatbot. Then in this scenario, the condition would be the input image and some other text some other text prompt that is given by the user. And the output would be the response of the chatbot based on this image and the text prompt. Let's say in this scenario, given this image, the user could ask what is unusual about this image, and the chatbot can try to come up with some answers about this problem. And it says it is just unusual to iron clothes on an ironing board attached to the roof of a moving taxi. So in many other real-world problems, such as robotics, we can also formulate the problem of policy learning as a generative model. So, for example, in robotics control, there could be many plausible trajectories, many plausible policies that can fulfill the same task. So, in this case, for example, you want the robot to move these T-shaped objects into their target location. So the robot could either move from the right-hand side or it could move from the left-hand side. So both trajectories are plausible. So there is no single unique answer. So then this is why, this is also where we can use generative models to model this policy learning problem.
Unexpected sweat can ruin a perfect look.
Oh, yeah.
But Secret Whole Body Dry Feel Deodorant absorbs sweat without aluminum for 72-hour freshness everywhere.
I know a secret girly when I see one.
Secret, no sweat.
So in general, this is what we have just seen. So a generative model conceptually just care about this conditional distribution. So in my opinion, actually, there is no any constraints or requirements about what can be X or what can be Y. So conceptually, they can be anything. So that means we can use generative models to solve many kinds of real-world problems. We can just try to formulate all these real-world problems as kind of conditional distribution problem, and then we can try to apply the latest advance in generative models as a tool for this problem. So this is also partially why generative models is becoming more and more common today for people to solve real-world problems. So this will be the last slides of this talk, but I just want to give some of the high-level idea and convey some of the most important messages in my mind. So as we have seen, generative models have some deep neural networks as they are building block. So this is just like deep neural network have some layers as they are building blocks. So 10 years ago, the research in deep learning has been mainly about these layers. So let's say convolutions, activation functions, normalizations, self-attention layers, etc. So that is the research about 1 decade ago. And then we have generative models, and generative models becomes the next level of abstractions. All previous research on deep neural networks still applied, but there is a new level of research that would be built around generative models. Then moving forward, when people use these generative models to do more amazing stuff, let's say large language models, reasoning, and agentic machine learning, which we will cover in the remaining parts of this talk. In this case, these existing generative models would become another level of building blocks. So as we can see, and as you have seen from Philip's introduction slides, we are building a stack of many different levels of models. So these are different levels of abstractions. So the abstractions could be layers, could be deep neural networks, they could be generative models, and they could be reasoning agents. So this is just like how computer science has progressed over the last century or so. So people are building different levels of abstractions, and then we can unlock different levels of new opportunities. So in this sense, I would say, so generative model is the next level of deep learning, and it's also the next level of abstraction and building blocks. And with that, that is the end of my talk. You mean generative models is inferior in the simple task of supervised learning?
Yes.
I think there is no certain answer yet, because in some sense, I think it is not yet a common understanding that you can address a discriminative problem using generative models. So if it is a very easy, let's say, closed vocabulary classification task, if you very clearly know that you have 10 possible labels or 1,000 possible labels, then usually a simple solution is sufficient. But even in the case of the so-called open vocabulary recognition, let's say you will be given one image, you still want one label, let's say a hashtag, then you can still have a vocabulary, but that vocabulary is just the English vocabulary, the human vocabulary. It could be very long. And even in that case, I think a generative model is a good idea. Then if you want to move one step further, you want to have a sentence as a description, or if you want to have some conversations that is based on this image, then generative model is perhaps the only solution that you should use.
So tell us what a biohybrid interface is.
So a biohybrid neural interface is when we take heavily engineered stem cell-derived neurons in a dish, we load those into the electronic device, and then what you place into the brain is just the engrafted cells. So we're not placing any metal or any, like no electronic or mechanical component goes into the brain.
Instead, you're growing
all we do
neurons
is, we basically graft these cells onto the brain through an appropriate starting point, and then those grow out, form new connections, just as kind of more of the brain.
And this is because Mother Nature is really good at growing cells into groups of other cells and so on. So you're taking advantage of that.
Yeah, we're letting biology do as much of the heavy lifting as we can.